All right, good. So you have to learn lots of languages and frameworks, and there's so much to learn if you want to go across the full stack. Normally, these things are split across multiple teams, but if you're working by yourself or on a small team, you're going to have to learn something new other than Android. In particular, if you want to set up your own traditional backend, setting up your own server, there's the issue of configuration. So how do you get your Linux machine configured and set up? This is rather taxing to do. There's also maintenance, so installing patches, making sure that your servers are secure and resilient to attacks. And there's also scaling, right? So it's not just enough to set up one machine. You might have to set up many machines to handle all the load that your app is going to generate. And then when your app becomes decommissioned, which is often the case for games, you also have to figure out how to scale down. So all these things are really just kind of not within the realm of what application developers typically like to do. But that's okay, because there are services out there that will give you a backend as a service where you don't have to worry about the management of servers. So Firebase is Google's mobile application development platform. It will help you build better apps, improve app quality, and grow your app. There's 3 different pillars. I'm mostly concerned about this first pillar, the handful of products that provide the backend to help you build the basic functionality of your app. The main components of this are Firebase authentication, which lets you get your users identified and signed in, Cloud Firestore, which is a cloud-hosted, massively scalable real-time database, and cloud storage, which is large binary object storage, like pictures and PDFs and things like that. Now, the interesting thing about these products is that you can directly invoke them from your client. So you don't need any sort of backend component to work with these. You just write the code inside your app, and it all just works without having any sort of middleware between the client and the server. But there are some things you really don't want to trust in the client app. And I'll point out that with Android and iOS and web apps, everything can be reverse engineered. All of the code is effectively mutable. You don't control the device that they run on, so you shouldn't actually trust the code in your own app. And I know that sounds weird, but that's a major security problem. So if you're doing things like payment processing, you probably want to put that code on a secure backend you control. Things like game logic, you don't want people hacking your games. You want to put the logic into that in a secure backend. Data validation should never really be done solely on the front end. The front end can do some validation, but you should never trust the data coming directly from the app. That should be in a backend where you control that. Scheduling periodic work is also kind of problematic for mobile clients, because you really can't trust the clock, and you can't really trust the world of mobile applications to schedule periodic work that should happen daily or hourly. And also batch data processing. Mobile devices just are not good at dealing with large amounts of data, so if you have batch jobs, that should definitely be done on the back end. So there's a bunch of things you really shouldn't do in your app. You should do those in a backend. Now, Firebase by itself, with database authentication and cloud storage, is not really sufficient. You need a backend component where you can deploy code and run that on the backend. So if you are a front-end developer, you probably have a preference about what you would like to do on the backend. You would probably like to minimize the time and effort to a solution. So you probably don't want to spend a lot of time learning new things. You want to minimize maintenance, all that stuff I talked about before, configuring and setting up your server. You just don't want to do that. You probably want to make use of what you already know. So if you're an Android developer, you know Java, you know Kotlin, you'd rather keep doing Java and Kotlin if possible, but you will have to learn something new. So on your backend, you probably want to use typical JVM technologies. You probably want to use Gradle to build it, Dagger for DI, but you still might have to learn something new, and that's okay. The point is to minimize the amount, minimize the friction to get started doing backend programming. Now, I'll say that, and this is kind of my opinion, but this is the general advice, is that the easiest backends you can set up are serverless, and I put serverless in quotes. That's kind of a buzzword. The fact of the matter is that with serverless cloud computing, there are still servers. You can't get rid of the servers. All you can do is sort of sweep them away so that you don't have to manage them so much. So with serverless cloud computing, there's no licensing, no installation, no maintenance. All of that is handled by the cloud provider, so you do nothing in that respect. Also with serverless cloud computing, the implication is that you pay for only what you use. So if you're using a database, you only pay for the queries you actually make. You don't pay for some backend to be running 24/7, even if you're not using it. So serverless has a huge advantage in being able to sort of minimize your billing. And it automatically scales up to whatever the load is and down to 0. So you don't have to have all these servers standing by. The idea is that the servers are allocated for you dynamically on demand, and then they go away when the demand is no longer there. All you have to do with the serverless backend is just write and deploy code. That's kind of the promise of serverless. Your build only when that code runs, and it scales automatically. So the first product I'd like to talk about is actually one of the oldest Google Cloud products. It's called Google App Engine. With Google App Engine, it launched over 10 years ago. So it's fairly old. It's mature. You can run Python, Go, Java, JavaScript, PHP, and Ruby backends. They're all relatively functionally equivalent. What you do with the Google App Engine is you build a traditional REST API backend. And that REST API backend can access some number of backend services provided by App Engine. So App Engine has things like full text searching, databases, memory caching, stuff like that. The components you would normally use to build out a backend, those are services that you just use programmatically. So you don't really have to set up and configure them, you just use them. Now with Google App Engine, you should be aware it has limitations. It is a 10-year-old product, so you can expect that it's, relatively behind the times. Now that said, it's still relevant. It still works. It's still being maintained. But my opinion is that there are better options out there, and I would like to focus on those. The first one I'd like to talk about is Google Cloud Functions. So with Cloud Functions, it's considered functions as a service. So with FaaS, what we're saying is the function is the unit of deployment. You're writing a function to be invoked in response to events. You write and deploy that function. There are two types of functions in Cloud Functions. There are direct invocations, so a traditional HTTP endpoint that you invoke directly from your app. There's also product-specific event triggers that happen in response to things that happen within specific products. Now, there are a couple of runtimes you can choose from. There is JavaScript running in a Node.js environment. There's Go, Python, which is very popular. And this is actually very new. There is a JVM backend. This is actually, I think, just a few months old. I believe it's in beta right now. And yes, because it's a JVM, you can run Kotlin in it in addition to Java, and the entire suite of JVM libraries. Everything on Maven Central is available for you to use, which is very convenient. Now, I'm going to talk to you specifically about Cloud Functions for Firebase. So Cloud Functions is a Google Cloud product, and it's part of the core Google Cloud offering. Firebase adds tools and APIs to that. So the Firebase team is actually kind of opinionated about the shortest, easiest path to use Cloud Functions. So with Cloud Functions for Firebase, you're getting a CLI. You can write and deploy functions in JavaScript or TypeScript, and that's going to run in a Node.js environment. This is really the only supported configuration. All those other runtimes I mentioned, so JVM, Go, and Python, those don't work with Cloud Functions for Firebase. So Firebase is being opinionated and saying JavaScript and TypeScript is probably the easiest thing for most developers, probably most web developers. We'll talk about some alternatives to that. They're thinking, I don't want to learn a new language. You said JavaScript. You lost me at JavaScript. I don't want to do any JavaScript. And you know what? I feel you on that one. I don't like JavaScript either. I think it's a terrible language and no one should ever have to write it. But that's okay because JavaScript has gotten a lot better over the years. There's a new language called TypeScript, and I see it as a better JavaScript. TypeScript is a superset of JavaScript. So all JavaScript programs are valid TypeScript. And TypeScript takes JavaScript and adds language features to it to make it much more pleasant to use. So TypeScript adds a sophisticated static typing system. So you don't do away with, but you add on top of JavaScript's duck typing a more proper, strongly typed static typing system. You get generics. So your lists and your maps can now be genericized to make them much easier to work with. Interfaces, which you know from JavaScript, which you know from Java, are also present in TypeScript. There's also nullability guards. This is huge. Everyone knows that functions that return null are very problematic to work with. It's just the same way in JavaScript and TypeScript as it is in Java. Kotlin adds nullability guards. So does TypeScript. The compiler will catch you if you don't check for null or undefined properly. And there's community support for existing JavaScript modules. So if you want to use a library that was written originally in JavaScript, chances are very good that the community has written TypeScript bindings for that so you can work with it in a strongly typed environment, which is super handy. And that's called definitely typed. So if you're using a library that doesn't have native TypeScript bindings, go to the internet, you'll find one. Now, all of Firebase's APIs do come with TypeScript bindings. So I have no problems working with that. I like it a lot. So let's look at a typical class in Java just to compare how these languages work. So here's a typical class, some properties, actually members, and a couple methods on that with the constructor. The equivalent TypeScript code is almost line for line equivalent. You should have no problems following along with that TypeScript. So instead of saying final, you say read only. Instead of calling the constructor by the name of the class, you just call it constructor. You access members with this. You have methods that look and act pretty much exactly like their Java equivalents. If you wanted to work with that class, here's what some Java would look like. You can new up a rectangle, use the properties on that, and then print out a message. The TypeScript, again, is very similar. You new up that object. You compose a string. You'll notice that there are back to quotes in the message string. I don't know if you can see that. And then the log message is pretty straightforward. Now, if you want to do this in Kotlin, of course, you can compress this down even further. So with Kotlin, you can define a class. You can eliminate all of the members. They're just there in a sort of constructor style definition. So you're compressing down the code. I mean, for the most part, all of these languages, Java, TypeScript, Kotlin, kind of look the same to me. Now, I've picked kind of a trite example. Of course, things get more hairy as you get into things like I/O and networking. That's where the languages start to diverge a bit. But my point is that TypeScript is not that hard to learn, and it's much more pleasant than working in JavaScript. And so if you want to use the Firebase tools, I strongly urge you to look into TypeScript. Now, one of the things about TypeScript is that if you use an IDE, now this is a Visual Studio Code made by Microsoft. TypeScript is actually a Microsoft language. If you're using this as an IDE, you can see that there's IntelliSense completion. So at the bottom where you see await snapshot.ref dot, you type that dot. If you have TypeScript bindings, you get help on what the properties and methods are that are available to you. This should be familiar to you as an Android developer. It's really no different. It's basically saying the compiler looks at the object, knows what's there, gives you your list of options. Let's say you want to choose update, so it fills it in for you, and now you have help in the IDE. This is TypeDoc, just like JavaDoc, just like Kotlin's documentation. Everything is inline in the IDE, which makes it really easy to learn APIs you don't already know. So with all of this IDE help, TypeScript should not be a very far jump from your existing Java or Kotlin experience. Now, if you want to apply this to Cloud Functions, if you want to write one of these HTTP functions that you invoke directly from your client, using the Firebase APIs, what you get is a situation where you can emulate Express.js for simple functions. Now, if you're familiar with the Node.js environment, Express is that HTTP framework that you work with. It's ubiquitous among all Node developers. All you really have to learn is its request and response objects, which are not so far out of the ordinary that, I mean, they're just not difficult. Now, if you want, you can provide your own full Express.js app. You don't have to do this, but you can. So here's a simple example. Here, what I'm doing is importing the Firebase Functions SDK. I'm going to use that SDK to build an HTTP function. So what I'll do is say functions.https.onRequest. That onRequest says when there's an HTTP connection incoming, I'm going to get a request and a response object. I can pull query strings and request body objects out of that request, and then I can send the response. Pretty straightforward stuff. This is your typical hello world. To deploy this code, all you have to do is use the Firebase CLI to say Firebase deploy. It will do some work. It's actually doing a lot of work behind the scenes, stuff that you would normally have to do yourself. I'll go into that a little bit more detail later, but it's suffice to say it's doing a lot of work for you. And at the end of that, you'll get a URL. You can see that the URL is based on the region of deployment. So US Central 1 is a Google Cloud Platform region, the default. Your project ID is in there, whatever your unique ID, then cloudfunctions.net, and then / the name of the function. So in the function, I exported it as echo. Here in the path, it becomes echo. So pretty straightforward URL. And then you can use curl on the command line to invoke it. You can pass a query string argument, and then it will echo back what you said. So getting started with the hello world is pretty dirt simple. Like, there's not much to it. Of course, your code will be more complicated, but the point here is that there's very little to learn to actually get started. Let's see. So it gets even easier than this, though. Firebase has this notion of callable functions. So what I showed you is an HTTP function where you manage the details of the HTTP transaction. Callable function goes further and says, I'm going to wrap all of the details of HTTP and give you a super simplified interface. So Firebase provides SDKs for client apps, both Android, iOS, and web, and the derivative SDKs for like Unity and C++ and so on. And then there's the backend function SDK as well for JavaScript or TypeScript. So it's giving you SDKs to work with. These SDKs will automatically handle all the details of the HTTP protocol. In fact, you never see anything related to HTTP in your code at all. It's all just managed. On the client, what it will do is automatically send a Firebase authentication ID. So if you're using Firebase auth to sign in a user, the SDK will automatically pick up that user, send an auth token, and make that available to your function so your function knows who invoked it. It's also going to send a device ID token that you use for Firebase Cloud Messaging. It's also going to serialize the input object you provide and deserialize the output object in the function. So you don't even worry about JSON. The JSON serialization is all automatic. All you do is say objects in, objects out, and that's it. On the back end, when you write the function, it will automatically validate the auth ID token so you know the UID that you have is secure. It will also do the serialization that I talked about. So callable functions are doing a lot of work that you might have to do normally and providing a convenient wrapper around that. So let's look at a simple example. If you want to write a callable function, let's start on the back end in TypeScript. What we'll do is import the functions SDK again, say functions.https.onCall. On call is different than before. Before we had on request, now we have on call, and we're saying it takes a data input argument. We don't know what that is yet, but it takes an input, and it's going to assume that there are two properties on that data input, A and B, and then just return an object that contains the sum of them. Again, a really, really tried example, but you can see how it works. So we're just objects in, objects out. That's all we're doing here. Then on the Android side, if you're writing Kotlin, what you would do is create a map with those properties. So this is just a standard Java or Kotlin map. So we'll have a property A and a property B with values 4 and 5. Then we'll use the Firebase functions SDK, access the HTTPS callable called sum. So the sum that you see here in quotes is the same as the exported name from the function. And then we'll call that with the argument. Now that argument, that map is going to be, as I said, automatically serialized. So you don't have to do any work to get that over the wire. The SDK is doing all the work. Then there will be a response. You add an onComplete listener, which is an asynchronous callback. You'll get the callable result. And all you have to do is reach into it in the way that you would normally expect. Use the data property, cast it to a map. We're expecting a map back, so we'll just cast it and then print the result. And then if there's an error, you can handle that as well. So pretty simple example, but you can see how easy it is to get started. There's no details of HTTP in here at all. The only mention of HTTP is in the name of the methods that you're calling. Other than that, everything is handled, so it's super easy. Now, those are HTTP triggers that you invoke from your function. There are also event triggers that run in the background. We call these background functions sometimes. So it's important to note that Cloud Functions is event-driven. And what this means is you have some number of event providers out there. These are either Firebase or Google Cloud products. They are going to emit events when things happen within those products. They're going to get corralled by Cloud Functions, the product Cloud Functions, and then it's going to turn around and trigger your function code that you have deployed. That's how it works. Cloud Functions is entirely event-driven in this respect. So if you want to write a background function that triggers when some events occur, what you have to do is indicate the Cloud or Firebase product or the event provider, the type of change you want to process. So for database type products like Cloud Firestore, it could be whenever a document is created, deleted, or updated. You just specify what is the event that you're looking for. You might have to specify a pattern to match for that change. So if you're looking for database changes, you might have to call out a specific location in the database that you're interested in. And then you write the code to run in response to the change. So that's basically what you're doing when you write background functions. Now, these functions trigger asynchronously after the change occurs. So you can't intercept a change. That's not possible here. You're responding to the change. So a short list of Cloud Functions event providers are probably products that you already know about or heard of. For example, there's Cloud Firestore and Real-Time Database, the two databases that are part of the Firebase platform. Cloud PubSub is Google Cloud's message publishing system. So it's like a message queue, basically. This is how you glue together different parts of Google Cloud Platform. There's Cloud Storage with this binary storage, Crashlytics, which many of you are probably using. You can write code to trigger when there's a velocity alert, and so on. I won't go into all of these. So let's say you want to write a Firestore trigger. So again, Firestore is Google Cloud's massively scalable, real-time, NoSQL database. So let's say you want to write a function here. What we're going to have to do is use the Firebase Functions SDK, call out Firestore as a product, and then give it the pattern of a document to match here. So here we're saying there's a collection called messages, and that ID in curly braces, that's saying we're interested in any document that's created in the messages collection. That's what we're telling Cloud Functions here. And then inside our callback, what we're going to do is get a snapshot. That snapshot is going to represent the document that was just created. We can reach into it, get the data out of it, pull fields out of that document, cast them or make assumptions about what's in there as necessary. In this case, what we're going to do is rewrite the message to replace the word cat with a cat emoji. So I don't know, this could be kind of fun if all of your cats became cat emojis in your document. Who knows? And then we'll write that back to the document. So again, this is, and I am the master of really useless tried examples, but I hope you had some fun imagining what the word cat would look like throughout your database. And by the way, this will capture not just the word cat, but catatonic, catapult, catamaran, and so on. So this is actually kind of a bad regular expression. We need something a little better than this. But the point is, you can make very dynamic changes to your products by writing a little bit of code to process events that are incoming from them. Now, another thing to note about this code sample, and again, this is TypeScript, is that we're using async await syntax. If you're going to write TypeScript, you're going to have to learn how promises work. Promises are a lot easier to understand when you're using async await. If you already understand Kotlin coroutines, promises are very, very similar. So async in JavaScript and TypeScript is similar to launch in or starting a new coroutine context. Await is similar to working with a deferred call. So update actually returns a promise that resolves sometime later after the work is actually done. If you await it, what you're doing is pausing this thread, this coroutine, if you will, until that's done, and then the function finally returns after all that work is done. So this is the major sticking point for learning JavaScript and TypeScript, is proper handling of promises. And if you've spent time learning how coroutines work, you probably went through a similar kind of thinking. It's the same kind of thinking. So what do you have to know to use Cloud Functions for Firebase using JavaScript and TypeScript? You're going to have to learn some minimal Node.js. You're going to have to learn NPM to get software packages installed into your project. This is pretty straightforward. You're going to have to learn JavaScript or TypeScript, the language itself. If you have a background in web, this should come very naturally. You're going to have to learn asynchronous programming with promises. And again, I can't stress this enough. This is the number one hangup that developers who are new to Cloud Functions and new to TypeScript and JavaScript, this is the biggest problem. Once you get past this, everything is very easy. If you're going to write HTTP functions, you should know a little bit about Express.js, just as that request and response object. You don't have to know them in detail, just enough to know how to process the incoming request and how to send the response. And you're going to have to know a few Firebase CLI commands, like Firebase deploy. So that's kind of the sum of what you need to know. When I was with the Firebase team at Google, I did a bunch of video tutorials. There's a bunch of sample code available. There's a code lab you can go through that will walk you through it step by step. My repo, my personal GitHub is full of Cloud Functions examples. The video tutorials, I will say, if it's all me. If you haven't enjoyed listening to me and talk and looking at me so far, you're probably not going to like the videos because it's all still just me. But I think they're helpful. I think you might find them helpful too. But you're thinking, I still just want to write Kotlin on Cloud Functions. Now, I'm trying to sell you on TypeScript, and you don't have to buy it. If you still want to run Kotlin, that's fine. You just have a different path to learn, but it's the same core product. If you want to run Kotlin on Cloud Functions, Firebase provides no tooling for that. You're going to have to jump into Google Cloud land and run gcloud. Gcloud is their CLI that does a lot of the same things that the Firebase CLI does, but it's far more complicated. There's a lot there because it's the tool to use to manipulate all of Google Cloud Platform. You have to build a jar. That's easy enough, right? If you know server-side or desktop Java, you can build a jar, no problem, and deploy it with the CLI. So there's really not that much to do. The devil is in the details of using gcloud and how to build that jar. So if you're going to build your function with Gradle, the minimal build.gradle to get started is pretty simple. All you have to do is apply your Kotlin plugin, use a standard library if you want, probably want to. That second dependency is the thing you need to know. When you add this, this gives you the APIs to work with Cloud Functions from a JVM perspective. The APIs are all Java, but you can certainly use them in Kotlin, no problem. Your source code goes in source/main/Kotlin, much like it would if you were on Android. And there's more you can add to your build.gradle for local testing. So you can test your functions locally. You just have to add some more stuff to your build.gradle to set up the invoker for that. And this is all covered in the documentation. I won't cover it here. So if you want to write an HTTP endpoint that's similar to the one I showed you before for TypeScript, all you have to do is import a few things from the Cloud Functions SDK, you declare a new class, have its subclass HTTP function, and then you override the one method in there, service. Service takes an HTTP request and an HTTP response. You do what you need to do with the request and send the response. Pretty straightforward stuff. Here's a hello world. If you actually want to get this code out there, all you have to do is run the gcloud CLI. Now you can see this gcloud CLI is a bit more complicated than the Firebase CLI. What you have to do here is gcloud functions deploy, give the function a name, I'm calling it hello, tell it the name of the class to use as the entry point, so that's the hello world that I showed on the last screen. Call out a runtime, in this case we're running in a Java 11 environment, it's an HTTP trigger, and because we want this to be accessible to our app in public, we have to say allow unauthenticated. If you did not say allow unauthenticated, it would only be accessible inside the project that you're working with from within other Google Cloud projects. So you have to pass a bunch of arguments here. I usually put this in a shell script. You can do whatever you want. What this command will do is it will upload everything from the current directory where you run it. It will send that all to Cloud Build, which is another Google Cloud product. Cloud Build will effectively run the commands that are required to build your project. So it actually sees that it's a Gradle project automatically. You don't have to tell it. It just says, I see there's Gradle in there. I'm going to run Gradle W clean assemble to build that jar. And then it takes that jar and puts it into a Docker image. Now, the Firebase CLI is doing this too, but when you run it through gcloud, you actually see the details of what's going on with building the Docker image. If you don't know what Docker is a sort of like a virtualized server builder. When you build a Docker image, you're building something that contains an operating system like Linux, all of the libraries that are needed, all of the code that you need to run on top of that. And it creates this one Docker image that ends up being deployed to Cloud Functions, and then it ends up sending that over. So there's a lot of complexity going on here, both in gcloud and in the Firebase CLI around building that Docker image. Cloud Functions makes it super easy because you don't have to know anything about Docker at all to make this work. Now, I will talk about a product later, Cloud Run, where you do have to know Docker, but suffice to say, for Cloud Functions, minimal information is required. So like I alluded to, actually, I didn't realize I was on this slide already, but Cloud Run is another product that I'll talk about, the last product I'll talk about that is also considered serverless. Cloud Run is serverless in that it has the same runtime behavior in that it scales up and down automatically. You don't manage any server instances. But what's required with Cloud Run is a Docker image. You have to know how to build this. You can't lean on the Firebase CLI or the gcloud CLI to do this for you. You have to know how to build this image. And you implement HTTP endpoints within the code running in that image. So you have to bring your own software to implement those HTTP endpoints. Now, with Cloud Functions, I mentioned there are event triggers that let you trigger on things that are happening in various Google Cloud products. Right now, no such thing exists for Cloud Run, except you can proxy pub/sub events in there. But there is a new thing in progress right now. It's called Events for Cloud Run. It's in private alpha. They want to take the events that you can use to trigger Cloud Functions and bring that into the Cloud Run environment. So if you can find the private alpha and sign up for it, by all means do that. But if you're not in that private alpha and you want to use Cloud Run and you also want to process events from other products, you could bridge events from Cloud Functions. So the idea is you can write a Cloud Function that handles the event and then turns around and proxies that to Cloud Run. So the actual work is being done by Cloud Run, even though it was initially handled by Cloud Functions. And with Cloud Run, you can use pretty much any language and runtime you want. You are not limited at all, except by what Docker image you can build. So if you can build a Docker image that handles the request in the language and runtime you want, by all means, go nuts, do whatever you want. So if you want to do a backend in Kotlin, so if you want to build a Docker image using Kotlin to handle HTTP requests, I'll show you how to get started with a build.gradle. Now, I will say that the Cloud Run documentation does give you a lot of help getting started building a Docker image and getting started with Gradle. I took what I did not like what was provided, and I modified it heavily. At the end of the day, you're going to either copy what I have or copy what someone else has. You don't have to generate this all from scratch. So what you're going to do is apply the plugin Kotlin, which you already know, apply the plugin application, which is a Gradle plugin that lets you build standalone apps that you run on the command line. You're going to need a couple dependencies, the Kotlin dependencies, and in this case, I'm going to use a web server called ktor. Ktor is a Kotlin native web server. So what I'm doing is setting up this web server. I'm going to have to write some code to hook into it to tell it to handle requests on a high port and then to trigger my function, trigger my code when that request happens. I'm going to have to declare the main class, the entry point for all of my code. So there's going to be a main class, and I'll show you an example of that later. And you're going to have to tell it how to build a jar. So in this case, I want to build a jar called app, and I want it to have a manifest where I give it the main class name. So this jar file has to have some metadata in it that tells it, where is the main class? Where do I start? Where is my public static void main? And then I'm going to also tell it to pull in all of the dependencies into one big jar. I'm creating kind of an Uber jar here. Now, this is one way to do it. I have some sample code. I'll give you a link to it later that uses shadow jar, which is actually a better way of building this. I should have updated this slide to show shadow jar, but all that's to say is you have to build one giant jar with all your software dependencies to install into your Docker image. Docker will not do that for you. You have to write the code to do that. So once you have a way to build an application, next you're going to have to build a Dockerfile that says how to build the server image that contains your software. A sample Dockerfile looks like this. Now, I will say this is what's called a two-stage build. One stage is going to build the application. The next stage is going to install that application in a new image. So for the build stage, stage one, what I'm going to do is use an existing Gradle Docker image. This is a Docker image that exists somewhere out there on the internet that has Gradle and a JVM on it for you. So in this case, we're using Gradle 6.6. Actually, it'll use the greatest minor or micro version. So at the time I'm talking right now, it'll be Gradle 6.6.1. It's also running it in a JDK 8 environment, so Java 8. We're going to call this stage builder. So the builder is going to be used to actually just build the jar file. What we're going to do is take the build.gradle, take all those sources and copy them into this new container image. Then what we're going to do is run Gradle to first clean and then build the entire project. So the no daemon argument is necessary to make sure that Gradle blocks and does not leave a daemon around so that we know when the build is done. This is going to build that fat jar, and it's going to put it in /home/gradle/build libs app.jar. That's our destination jar file. We need to know that path. Then in stage 2, after the build is done, we're going to start up another new Docker image. It's going to use OpenJDK, Java 8. You can use any JDK you want. It's generally advisable to use a trimmed down Docker image or a JVM image that works well with Docker. This is one that Google Cloud recommends. You can do your research to figure out which one you actually want. But you have to know one. You have to figure out where your starting point is. And then into this image, we're going to copy from the builder stage the file that was generated during the build stage, and we're going to drop it in app.jar in the root folder. And then we're going to say, in this Docker image, when we launch this Docker image, what's the command to run to kick things off? So in this case, we're going to have to run the Java command that tells it to run app.jar. And so this is all we need. So there's one Docker file, 2 build stages. The second stage is actually building the image that runs your jar file, that will run your web server and listen on a high port for web requests. Okay, so once your Docker file is done, you're going to have to actually write some code, right? Let me show you what the code looks like, minimally speaking. So the first thing you're going to have to do is define your main entry point. So in this com.example.hello, we have a new main.kt class. This main function is going to have to get the port that we're listening on. Notice that we're getting this out of the environment. Cloud Run defines that it will give you an environment variable called port, and you should listen on that high port. By default, it uses 8080, but you should really use the environment for this. Then what we're going to do is tell ktor to run a server on that port. So embedded server says, I'm going to new up a web server. I'm going to use Netty as an engine. There are different engines. Netty is just one of several you can choose from. If you know Java program, you probably dealt with Netty as a core networking component, and we're going to give it the port we want it to run on. So once this embedded server is started and blocking the process, what we're going to do is set up some routes. And these routes are basically the paths that you expect incoming on the web server. So we can say whenever a GET request comes in on a path called greet, what we'll do is respond saying hello world. So this is your hello world example. So this is really all you need to get started in Cloud Run. But you'll notice we had to put more details into build.gradle. We had to come up with a Dockerfile. We had to come up with this minimal hello world. So you can see we're doing a lot of configuration before we even get to the coding. So you can see that Cloud Functions is easier than Cloud Run, but with Cloud Run, you can do whatever you want. So once you have all this coding configuration set up, how do you get that into Cloud Run? Now, what I'll show you is basically a stripped down shell script. And this shell script is going to need 3 values. One is your project ID, that was assigned when you created your project, a service ID that you declare on your own, and you need a tag. And this tag is basically saying where you want your Docker image to live in Google Cloud Run. So what you're going to do is use the gcloud CLI to submit this build to Cloud Build. You will watch your app build. It will do so somewhat slowly. It takes a couple minutes for it to do that, which is a little bit frustrating. It takes a lot longer than I'd like, but it will do the build automatically. Then you can gcloud run deploy and give it the tag that you just built, the service ID that you want to deploy to. Platform manage just is saying, I want to use the Google Cloud managed platform as opposed to Kubernetes or some other platform. And allow authenticated is just like we talked about before with Cloud Run, where we want to allow HTTP access from the outside world. We'll do some more work. And then at the end of that, it will give you a URL that's your root endpoint for the entire image. So it'll be HTTPS followed by your service ID that you declared in your script, and then some random letters and numbers, and then .a.run.app. This is your URL. It's kind of ugly, but it is your URL. And all requests coming into it will go to your Docker image. So with Cloud Run, you really have to figure out what exactly do you want to run. I've shown you right now using Kotlin and ktor to build a simple hello world using HTTP. But at the end of the day, you can run whatever you want. So if you want to run ktor, that's fine. If you want to run nano HTTPD, that's fine as well. If you want to run a J2EE container, that's fine. Tomcat, Glassfish, whatever you want. There are actually server images for these. There are Docker images that give you the core framework for each one of these. All you have to do is find a Docker image and deploy to it. You have to figure out what framework you want, or even if you want to use a framework at all. You can use ktor and its sort of Rails for building functions, or you can use your own framework, whatever you want. What you have to know to use Cloud Run, just boiling it down. These are the things you have to know if you don't already know. You have to use a programming language or HTTP, programming language, runtime, and server of your choice. You will have to choose something and know them well. You will have to know how to build or modify a Dockerfile to create a container that contain all of this software you've written or are using. You're going to have to figure out how to integrate your backend code with that container. So you're going to have to figure out how to write the Docker code to copy your source code, build that, and build the Docker image. You're going to have to know a few CLI commands to get this all deployed into Google Cloud. So there's actually a fair amount to know here. I would say that Cloud Run is the difficult path to get started, but it's still much, much easier than trying to set up and maintain your own server. It's another thing that's nice to know is how to test your container locally. Since it is fairly taxing, time-consuming to build a new server image and deploy it to Google Cloud, it's helpful to know enough about Docker to test your Docker image locally. This will speed up your development massively, or even testing your code before you even build a Docker image. In my projects, I usually set up some IntelliJ, what do they call them, run configurations to run your web server locally so you can hit it and make sure it works the way you want before you even touch Docker. So let's compare Cloud Functions to Cloud Run. I've talked a little bit about both, but at the end of the day, you might want to choose one or the other. How do you choose? With Cloud Functions, you choose a runtime. You have to choose one of the supported runtimes. You cannot go outside of these choices. You are stuck in the Cloud Functions choices, which are not bad choices, by the way. As I said, I like TypeScript, and you like, Java or Kotlin. That's fine. With Cloud Run, you can choose pretty much anything you want, both language and HTTP server. With Cloud Run, you have to write a Dockerfile. No such work needed for Cloud Functions. It does all that automatically. With Cloud Run and Cloud Functions, of course, you both write code. Then with Cloud Run, you have to build a container with that code added. Again, Cloud Functions does that for you. You do no extra work. With both Cloud Run and Cloud Functions, you run a command to deploy the code or your container. So actually, let me go back. So you can see that Cloud Functions is basically fewer steps, although you have fewer choices. With Cloud Run, you have basically infinite choices, but you do a lot more work to make that work, to make all that code happen. So it's up to you which one you want to choose. Now, I will say that Cloud Functions does not perform as well as Cloud Run. Cloud Run, at least in theory, it makes more efficient use of the virtual hardware that you're being allocated. So with Cloud Run, you can handle multiple requests at the same time in your web server. With Cloud Functions, each cloud instance is running one request at a time, so it's less efficient. So there are reasons to choose Cloud Run over Cloud Functions, but Cloud Functions is always going to be the easier choice. So let's talk about capabilities and limits. With Cloud Functions, of course, you're limited. With Cloud Functions, you're flexible. Cloud Functions is easier to set up and deploy. Cloud Run is more difficult. With Cloud Functions, you can only deploy code to Cloud Functions. So once you have all that set up, you're kind of stuck on Cloud Functions. Of course, you can take your code and rewrite it to run anywhere else you want. But in terms of deployment and infrastructure, you're baked into Cloud Functions at that point. With Cloud Run, since you're building a Docker image, you can take that Docker image and run it on any cloud that you want. Pretty much all major cloud providers give you some way to run a Docker image. So once you know Docker, that gives you the flexibility to take that image and run it on any major public cloud. But with Cloud Functions, there's the distinct advantage that you can trigger events or trigger on events from Firebase and Google Cloud products. That's the advantage of being in the Google ecosystem, is that you have the ability to trigger on events that are happening. With Cloud Run, you can trigger primarily on HTTP, but again, you can proxy events from Cloud Functions. Now, as I said, this is going to change. There is a new product in play called Events for Cloud Run, where they want Cloud Run to be able to process incoming events, but that's in private alpha. Now, I will make one more point about this in case it wasn't already clear. Serverless products scale up and down with load. Both Cloud Functions and Cloud Run both do this because they're serverless. The idea here is as you have users applying load to these products, you get servers allocated automatically. You go from 0 to 1 without paying any additional cost. As the users scale up, your server instances scale up. And this just keeps going as high as needed. In fact, I believe with Cloud Functions, you can have up to 1,000 server instances running. There is a practical maximum, but you'd be hard-pressed to actually find that maximum. I think it scales up very well. If for some reason it's not scaling up well for you, then you're probably doing too much work in your function and you need to offload that work into Compute Engine or something that's more suitable for very high volume computations. And again, not only does it scale up, but it scales back down to 0 as needed. And you do no work to make this happen. This is really the major value of using Cloud Run and Cloud Functions, is that you don't have to do any of this DevOps work, none of this infrastructure work, none of this configuration work. You're just writing and deploying code. And with Cloud Run, you're managing a Docker instance. Now, I will say, as much as serverless backends are very, very handy, they're not good for everything. So I will point out that serverless backends are not good for jobs that require a lot of time, CPU, or memory. The reason is that Cloud Run and Cloud Functions are effectively using commodity hardware to scale up massively. With Cloud Run and Cloud Functions, you're typically writing glue code that takes requests from the end user and does some database work and proxies it back. That's like the #1 use case, is just simple middleware that does I/O and networking. If you have something that's more than that, you probably want to invest in a different cloud product or proxy your work from Cloud Functions and Cloud Run into that other more CPU intense environment. Now, the only exception is this: if you're able to break down the work into parts and divide and conquer it, then you can start to use Cloud Functions and Cloud Run a little more effectively. If you have jobs that require large amounts of local storage, these serverless products will not be good because they don't actually have any local storage. They're entirely memory-based. In fact, the only writable part of the file system is temp, and that temp is backed by memory. So when you're writing files into temp, you're actually just writing into memory. So you're gated by the total amount of memory that you have in the instance to get your work done. So if you have to download a file that's gigabytes in size, you can try to configure an image that will fit all that memory, but I think like 2 gigabytes is kind of the maximum. So if you need a lot of storage and you need it all in one place, Cloud Run and Cloud Functions are not going to work well. If you need any sort of persistent socket I/O, so if you need to do web sockets, these products are not going to work for that at all. It's each request and response is handled as a payload in its entirety. So you have 10 megabytes to work with an input, and you have 10 megabytes to send back to the client. You cannot keep an open socket. You can't stream things back and forth between the client and the server. Also, large payloads will not work. So if you need to send more than 10 megabytes or send back more than 10 megabytes, again, probably not going to work very well. You can work around this by putting the content in, say, cloud storage or another place where a client can read and write directly. But over the payload itself, you have a limit, and that can't be exceeded. Okay, so that's all I have. I hope I was a little bit helpful in helping you get started being a full stack developer, managing both the front end and the back end of your code within your solo project or in your small team. Now, if you want to get a little more hands-on experience with this, go to this URL here. I have examples of writing a cloud function in TypeScript, writing one in Kotlin. Also, I have a Cloud Run example. There's a rather lengthy README that explains to you how to use those samples. And there's also an Android app that shows you how to call into the Cloud Functions and Cloud Run backend. In fact, there's examples for things like there's a little bit of architecture components in there. There's JavaX serialization. So if you want to serialize objects in and out of Cloud Functions and Cloud Run, you can totally do that in Kotlin. You can see examples in the code there. So that's all I have. I believe the organizers would like me to stick around and answer questions. I'm totally happy to do that. I believe that's going to happen in Slack. And so if you have questions, I will see you there. Thank you.
Awesome. Thank you so much. That information was so helpful. I'm sure a lot of us have run into having apps that were like, oh, wait, now we need a backend. What do? So thank you very much for that. We're going to push all questions to Slack and answer them asynchronously, if that's all right, just because we are running a little bit short on time and we want to make sure we have enough time to get prepped with the next speaker. So just as a reminder for everyone, you can share any questions that you have for Doug in Slack. We have the Slack channel that you can see at the bottom of the screen. Day 3, Doug Stevenson. So feel free to drop your questions in there. And once again, thank you, and we'll be back in 8 minutes with the next talk.